Well, hello. So today we're going to start Chapter 7, which involves gravitation. So we're going to look at taking our circular motion information from Chapter 6 and then relating this to gravitation as far as planets and even other objects' interactions with Earth. And so today we're going to talk about Section 1, which involves planetary motion and gravitation. And so the main parts involved with planetary motion and gravitation are Kepler's laws and then the Universal Law of Gravitation and how those two work together. There we go. Okay, so Kepler had 3 laws, and the first law was that the paths of planets are ellipses. So take a circle and kind of squish it down with the sun at one focus. And so as you can see from this picture, here's our sun. Oh, that's black. That's so boring. Let's do a different color. Purple. And so here's our sun. No, I can't find my marker. There it is. And then here's our planet. And so you can see that the sun is at one focus, or like one focused area of the ellipse. And then ellipses have 2 foci. So then we have this empty one over here. As you can see, the center of the ellipse is here, but our sun is in what's called one of these focus points, or one of these foci. And so as the planet orbits the sun, because it's not in the center, we get different speeds with which the planet goes around in this ellipse. So when it gets closer to the sun, we say that it has faster motion, and then as it gets away from the sun, we say that it's got the slowest motion. And that has to do with the pull of the 2 objects, the planet and the sun, and we'll talk in more detail about that in a minute. Kepler's second law is that there's an imaginary line from the sun to the planet, and then we break that orbit up into equal areas and equal time intervals. So as you can see from this animation, we've got the planet orbiting the sun. As you can see, when it gets closer to the sun, it's going to orbit more quickly. And when it's the furthest from the sun, it's orbiting more slowly. And even though these shapes don't look the same, they are the same size. And so we've got equal areas and equal time intervals, which is why that planet is going faster when it's closer to the sun, because it's got more area to cover. And so we're breaking this up into equal amounts. And this other drawing here, we've got the same idea. Okay, so area X, we may have a larger distance to cover, but it's also going to cover that more quickly, and it's also closer to the sun. And so area X, which is here, is going to be equal to area Y, and those distances are going to be covered in the same amount of time. So the first 2 laws deal with individual objects and their relationship to like the sun or some foci on the elliptical orbit. Kepler's third law has to do with more than one object. And so we've got an equation. So I've put all the equations in red, so this will help you if you want to put them on your note card. And so Kepler's third law relates the period of 2 objects with their distance from the main body, and so most of the time we would probably be referring to the sun as that main focus point. So the third law deals with the motion of several objects around one body. So if we have our body as the sun, and then we could be looking at the moon, the earth, a satellite, lots of other things that are orbiting that object. If we look at the body as the earth, then that would be the moon and a satellite. So planets would be orbiting the sun, and we can look at the relationship between more than one planet. Or if we're looking at the body as Earth, we could look at the moon and satellites and things like that. And so RA and R sub B, are the object's average distances from the sun. And so, for example, on this picture, we have them labeled as R1, R2, and we're looking at 3 different objects, so R3. Okay, so distance from the center of our main body to the center of the objects. And T sub A and T sub B represent the period of each object. So how long does it take each object to do one full rotation around whatever our main body is? And so this drawing could be more in relationship to, let's say, the Earth and different moons, well, for us, one moon, or satellites orbiting. And then if we take a look at this graph over here, we've got lots of different planets orbiting the sun. And so we can see how we've got a graph of cube of the axis. So angstrom units are distances that are much larger than meters because planets are so far away. And then the square of the orbital period. And so we've plotted the relationship of different planets. Okay, and you can see as the further they get, it's creating this slope. Okay, so now let's talk about Newton's law of universal gravitation, and then we'll talk about how they relate to each other. Okay, so gravitational force is the force of attraction between two objects, and it must be proportional to, and that's what this symbol here means, is proportional to the object's masses. Okay, so force is going to relate to the mass. So if you are comparing like an apple with Earth, like Newton's, when the apple hit him on the head, or maybe the relationship of the moon to the Earth, okay, so it's proportional to the object's masses. So the law of universal gravitation says that objects attract other objects with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. And so inversely proportional means we're putting it on the bottom of our fraction. And so another way to write this would be force equals G times mass object 1, mass of object 2, divided by their radius. And actually that should be squared. That should be a 2 on top. So make this a squared value, not a sub 2. Okay, and so what this means, let's take a look at the effect of the mass. Okay, we have two masses and their distance between them, and so we get a set force. If we increase the mass of either one or both of them, then we are increasing the force between them. Okay, now let's look at distance. And so that would, if we go back to mass, that would mean that the mass is proportional to force. If we increase mass, we're increasing force. Now let's look at distance. Okay, and so we have a distance between two objects. Now, if I increase that distance, see what happens to my force? I have decreased it by quite a bit. And that's where our inversely proportional to the square of the distance between them comes in. If we increase distance, we are decreasing force. Okay, and we can see if we have decreased distance, we have increased force. And then here we're changing distance and mass together, and so that gets a little bit more complicated. Okay, so the two main things you need to take from this are that as we increase mass, we're increasing force between the two objects, and as we increase distance between the two objects, we are decreasing the force between them. And then we put those two factors together to get the law of universal gravitation. G represents the gravitational constant, which we will get to in a minute. Okay, so if we take universal gravitation and Kepler's third law and combine them, we get this equation. And where T represents the period of the planet orbiting the sun, and so the time it takes for the planet to go around the sun one time. M sub s is the mass of the sun, and so this equation is in relationship to the sun. But if we were looking at a satellite orbiting Earth, then T would represent the time it took the satellite to orbit the Earth, and M sub s would probably become M sub e, which is the mass of the Earth, because the satellite is orbiting Earth, not the sun. R represents the orbital radius. How far is that object from the main body? So in this case, how far is the planet from the sun? Whoops. And let's rewrite this equation in something that's a little easier to look at. So period is equal to 2 pi times the square root of r cubed divided by gravitational constant times the mass of the body, which in our case is going to be the sun. So again, that's something you'd want to put on your note card. Okay, let's talk about how we figure out this gravitational constant, this capital G. It is really difficult to measure the force of gravitational attraction. We can talk about the relationship, like with the masses and the distance between the objects, but it's really difficult to get a set number for this gravitational attraction. And so Cavendish did an experiment to find that constant. And he found that the constant was equal to 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared. So when you're using this, you need to make sure your force is in newtons, your distance is in meters, and your mass is in kilograms. And that distance in meters part is probably going to be the most tricky because distances between planets are very large. So keep that in mind, and you also may want to put this constant on your note card. We can use this to determine Earth and really any object's mass if we know this gravitational constant. And the problem with Earth, though, is that because Earth weighs so much, it's really hard to measure the gravitational force between it and really small objects. So we've talked about this before when we talked about Newton's third law. If we drop like an apple, let's say, Earth is pulling on the apple, and the apple is also pushing back on Earth. But Earth doesn't spin out of orbit because the mass of that apple is so much smaller compared to the mass of Earth. And so because of that difference, it's really difficult to measure the gravitational force between them. So let's take a look at Cavendish's experiment. So what he did in general is he put this object on like a teeter-totter almost, and he used a string to hold it to keep it even. And so step one is that gravity pulls the apparatus down, and this is what we feel as the weight, the weight of the experiment. Okay, so this blue arrow here, I can't see my marker. This blue arrow here is representing that weight. Okay, then we've got this string to even out the teeter-totter and keep it from tipping one way. And so this string pulls the apparatus upward. This could be like the tension force, because that's the force in a string or a rope. And this keeps the experiment from falling. And so now we have countered or balanced out the force of gravity. So if we look at step 3, the two blue arrows are forces that exactly balance each other, so the experiment feels no force in the up or down direction. So basically we are balancing out gravity with an upward force. And now we're just going to look at horizontal. So step 4, I can't see my marker. As a result, the teeter-totter is going to rotate freely around the thread in response to small forces like the gravitational tug of another apple. So if I've got an apple sitting here and I've balanced out my forces up and down, if I put another apple here, it's going to cause a horizontal force between those two objects. Okay? And I can look at the relationship between the two objects without looking at up and down gravity. I'm only going to look at the horizontal force between them, and it's going to cause it to go in a circular motion. So I can experiment with putting my two objects closer and further away to look at the relationship of the force between them based on mass and distance. What Cavendish did more specifically has to do with this experimental setup up here. And so, but again, you've got your two masses and the distance between them, and we're using a light source to measure that rotational motion. Okay, so in class we're going to work on these practice problems, so please feel free to attempt them on your own if you would like. And then here is the homework, and you've also got all the answers on your outline. Have a good day.